And welcome to Lady Ada.
Wow! It's me, Lady Ada, and it's my desk. And here we are at the desk of Lady Ada. And we're at a late night on Thursday. It's a great night to do some debugging and some programming and some OpenOCD development, and we're going to be talking about that tonight. So if you're interested in running OpenOCD natively on a Raspberry Pi, you came to the right place because that's the topic of tonight's stream. I've been doing a lot more Cortex M0 hacking lately. I grew up kind of like on the PIC16F84 and 12C508, and then I graduated to like the Atmel At91s or At90 1200s or 2313s and then AVRs, and that was wonderful. But then I finally was like, you know what, I really want the power of a 32-bit ARM Cortex processor. And so I've been kind of, you notice that these streams there's been like every few streams there's been one about a Cortex chip. I tend to be hacking on the Atmel ATSEM-D21 because it's kind of like friendly, it's coming from Atmel, I kind of know how to read their data sheets. So, you know, I have these in the feathers, and I'm making a version of the M0, which is called the Metro M0, so this is like a prototype. And learning a lot about these chips, and one of the things that I've been learning is how to program them. Because if you want to do development, you know, you get the compiler you can usually get for free. You use the ARM AEBI compiler, compile your chip code for the Cortex M0, and you know whatever special registers you need for that chip. But then you have to get the code on the chip, like into the chip. And if you have a bootloader, yeah, okay, you connect to the bootloader and then use whatever bootloader tool. But if you're getting a raw chip, like from Atmel or from DigiKey, they don't actually come with the bootloader. Well, most of the time. I haven't seen any that come with the bootloader, although there are a couple chips like the LPC1343 that came with the mass storage bootloader, which is like super sweet. But Atmel didn't do that. I understand, you know, it's a little kind of weird to have a mass storage bootloader like burned into ROM. And so instead what you have to do is you have to program this chip with a programmer. Now, you know, I come from, again, like Atmel land, and, you know, I actually kind of designed the USB Teeny ISP for programming 5 volt and 3 volt logic. It's based on Dick Striefland's code called Teeny ISP. And the code to program, the protocol to program AVRs is actually just SPI. It's a really simple 4, you know, clock, data in, data out, reset, and you send like 8 bits and it gives you back 8 bits. And in the data sheet, it even gives you like a list of like, here are the 8 bits you send to read the fuse, and here's the 8, you know, 4 times 8 bits to write a fuse, and then you read flash, write flash, EEPROM. It's really simple. I mean, you can, you know, I've shown you can make an Arduino that will program chips with a bootloader automatically, and that's what we use for testers. You know, when we have a trinket or something and we need to program the bootloader in, we'll use an Arduino to do that because it's very, very fast. However, when you're getting to chips like that ATSEM-D21 or maybe the NRF51822 and other Cortex chips, you can't do that anymore. The protocol required to program these chips is called SWD, I think is single wire debug or something, simple wireless debug. I don't know exactly what it stands for, but it's a debugging and programming protocol. It's a 2-wire protocol, ground, clock, and data. The clock comes from master to slave, and then the data line is actually bidirectional. It's a little bit like if you've ever used 3-wire SPI. It's a little bit like that. You know, the controller, the programmer sends like the first like 3 or to 8 bits or whatever, and then it waits for a response. And it, you know, they both, of course, you know, they work back and forth to control and release the line. It's not I2C though, where like they use pull-ups and pull-downs. I think it's just straight up clocking and directional. But the commands are like really annoying and complex, and they change from chip to chip. And so instead of, you know, using something simple like a USB Teeny, you actually have to kind of upgrade and use something like a J-Link, which is actually a really awesome JTAG and SWD and SWO, which I don't even know, some other protocol. This is like a beast. So I got this quite a while ago. I think I got this back when I was in school. So it's the EDU version. There's also the base, which is the pro version. They're a couple $100, but it is the standard. Like if you're going to program anything that uses JTAG or SWD and you don't know how to program it, it's like guaranteed that the Sega J-Link supports it. And you can do firmware updates for life. So as new chips come out or they maybe find bugs and updates and improvements, you plug into the software and it'll like update. In fact, like pretty much every time I plug this in, it's constantly telling me there's a new firmware update your J-Link to support more chips, because this is pretty much what everybody uses. So that's the J-Link, but you know, you can get the educational version for $100. It's a good deal, but if you're doing commercial work like we are, and at work I have a bunch of bases, we use the J-Link base, which is a little more expensive. You can also, if your chip is supported by and it is okay to use it with, you can use the ST-Link, and the ST-Link is way simpler. It also does SWD, but it just doesn't have like every weird exception. Like really every chip company is a little bit different. And we use OpenOCD with the ST-Link, and it's a little dongle and basically USB in and then SWD out on these wires. And you can actually use this for the ATSEMD21 and the NRF51A22. It works fine. These are a couple bucks. They work great. And they're actually a little bit faster than J-Links sometimes. The only thing is once in a while, these get into like a weird spot, which I seriously don't understand what the deal is. It will like not be able to verify and actually have to unplug it and then wait a minute and then plug it in and then it starts working. So I don't know what the deal is, but like, yeah, they're $5. So you know, as long as you're not programming hundreds, you can probably get away with just using an ST-Link. It's 3-volt logic, and it's kind of nice. You don't have to feed the logic in. So these are the two options that we use now. I use the J-Link for development, and then when we go into like production, use the ST-Link. There's one other trade-off, of course. If you have a chip that has if you have a board that has two SWD devices, you can't like chain them, so you have to have two programmers. So you might like need two J-Links, and I'm pretty sure you can only use one ST-Link per computer. So that's something you kind of have to just think about. Like we have the M0 Bluefruit feather, and that uses a J-Link for the Bluetooth and an ST-Link for the SAMD. So I'm kind of learning this stuff, but that's fun. But so getting to where we're at now, so I'm trying to design some testers for some of the Feather M0 or at SAMD things. Like this is the Bluefruit sniffer. And it turns out that just the way the Nordic SPI API, the sniffer API Python software does its threading, and the FTDI driver in like El Capitan, you can basically test these on a Mac, but after like 10, like it kernel panics. So it's like, it's definitely like in the FTDI kernel driver and the threading, it's not releasing properly, and who knows. And I thought, like, you know what, this is a good opportunity to maybe see if I can get this all working on a Raspberry Pi, and maybe even get this chip programmed on a Raspberry Pi. So you like press a single button on the GPIO, and then it will program the chip, connect over USB, do the testing, and then like blink a NeoPixel or something to tell you you're done. So that's kind of where I'm at. That's why I wrote this tutorial. So with that, let's go to the Compi, and we'll go through this tutorial I wrote up, and you can follow along at home. Okay, so this is the tutorial. It's called Programming Microcontrollers Using OpenOCD on a Raspberry Pi. Very descriptive. So you got a Raspberry Pi, I've got a cobbler here, and then I use a little SWD pin breakout, because I use these fine 0.05 inch cables. Yeah, not a big deal. You just have to have a little adapter to match the, I'm trying to remember, it's like Target Point or something is the name, or Core Site is the name of this connector here. It's a very teeny little connector. So OpenOCD is just kind of an open source program that has a bunch of different chips and a bunch of different programmers, and it will kind of do the mushing together of figuring out how to get, you know, an ST-Link to talk to a Nordic NRF51822, or how to get a J-Link to talk to ATSEMD. Like it kind of has a whole bunch of chips built in. I did a slew of them. I'm not using all of them, but it does support these two, and that's awesome because these are the two I'm dealing with. And normally what you would do is, you know, you would go to Atmel Studio and, hold on, you would plug in your, can you do like a dual cam so you can see overhead and also this?
Yeah, which things do you want?
The overhead?
We got all sorts of stuff that you
All
can
sorts
do.
of stuff. Okay, this is fine. So I've got the J-Link, and then you've got this little adapter that just takes the J-Link, and you can tell I kind of just had to design all these boards, so I had all the accessories necessary to make this work. So you'd connect this to power this up, this device, and you plug this in here, and then so that's that's powered. That's connected to the J-Link. J-Link is blinking green. I guess that means it's good. I actually don't even know. I never looked up what the J-Link LEDs stand for. And then you go to device programming. You tell it, I'm using this J-Link. You tell it what chip. I had this all set up already because I was already programming a bunch of chips. You read the target voltage, and then you can read the device signature. And now you can get information about the device, and it will read, tell you what type chip it is, and it'll do all of, basically like Atmel Studio plus J-Link gives you like the most control. You can like set all the fuses, and it's like tells you the OTPs and like the temperature word or whatever. I don't know what that is. Security bit. Don't set that. We don't want to. There's like a J-Link control panel. It's just like you can set like the target frequency. It's just like a party. And if you have to do something special or you're trying to figure out what your settings should be, use Atmel Studio because it's going to have all the configuration that you would need. Not all the configuration bits and fuses are supported by OpenOCD. Just letting you know this isn't a replacement, but if you're in production, this might be good enough. So OpenOCD is nice because it's open source. So one thing is that J-Links don't work on Raspberry Pi. I think they have a Linux driver, but they have a Mac driver for sure. They have a Windows driver for sure. They have a Linux driver, but I think it's only Intel Linux. They don't have an ARM Linux driver, or if they do, it isn't compiled for the Raspberry Pi. I think I looked into it. I mean, it might have changed, so check again. That would be really cool if they added support. But you're dealing with basically a closed source system. It's cool, that's what Sega wanted to do, but it limits me a little bit, especially if you're using it with a platform that doesn't have the drivers. You can use the ST-Link, but like I said, sometimes the ST-Link kind of flakes out. It works well like 99% of the time, but I wanted something that was maybe all-in-one. So OpenOCD is a software, and what's really neat is someone added support for native GPIO bit banging of SWD. So instead of connecting a Raspberry Pi to a J-Link, you actually can connect just like the raw wires, which is like super cool. So instead of having this J-Link, and later J-Link, you connect this SWD wire cable directly to these GPIOs. And I'm not going to go through the compilation, just trust me, you do a sudo update, you compile it, you clone the latest code. I don't have a package for this because this is actually, OpenOCD is actually under active development. For tools that aren't under active development, I would usually make a Debian and be like, hey, from Adafruit you can download the latest Deb. I still might, but because it's under so much active development, they're constantly fixing bugs and adding new chips. I would actually just get the latest version, which is 0.10. And then you bootstrap it, and here's the fun part. When you configure it for compilation, you enter in /config -- enable Sisyphus GPIO -- enable BCM2835 GPIO. So that gives you two ways to do GPIO twiddling. One is Sisyphus, which will let you use the device. It's like /dev /sys /GPIO /import, whatever. Like it's the file system version of connecting to the GPIO, which is like supported by every single board computer. So if you're using this on like a chip, or you want to use this on your Banana Pi, you can probably do that. It'll probably just work fine, but it's a little bit slow because you have to go all the way around through this file system device driver. You're not going direct to the pins. And then with enable BCM2835 GPIO, what's cool about this is it actually memory maps the peripheral for GPIO and just writes the register, it just sets the bit, clears the bit, sets the output, clears the output directly, so you get ultra fast. You have to set the timings to tweak it because again, if you overclock it, you're going to change the I/O speed. Whatever. You'll have to figure out what I/O speed you need for your chip to get really fast programming, but not so fast that you don't program properly and you miss some of the bit transitions. You program this. It takes about half an hour on a Pi 2. I didn't try it on a Pi 1, but apparently I saw that there's a config file for the Pi 1 as well. So it will work with Pi1 as well. Make install, and then you will end up with this, which is like my Pi, which pretend like you already did this. So you went into OpenOCD and you did a make install, and you're like, yay, I did a make install. And then you can go into, whoa, hold on, copy, right? And these are all the interfaces that it supports. So you get to pick what chip, pick what interface. So we have everything from the Bus Pirate to the Bus Blaster to Flash Link to OLMX to OpenDeuce to OpenJTag to Hellshire, I don't even know what the heck that is, to that Sisyphus GPIO Raspberry Pi to the ST-Link, that's this little purple guy here. The Red Bee, R-Link Shiva plug, basically every system, you use a parallel port. You have a parallel port, use a parallel port. You can do anything that can basically do it, they will probably add support for it, which is pretty neat. And if you do Raspberry Pi 2 native, you'll see it actually sets up the peripheral base for the GPIO, and then, oh, can we go to the just compy, maybe? Because this is pretty small text.
Sorry, I didn't catch that.
No, that's cool. You set the peripheral base. So if there's a new Raspberry Pi, by the way, it's easy. Just figure out what the new peripheral base is by looking at the kernel or ask the developers, enter this in. You have to set the speed coefficients, whatever, figure that out, depending on the clock. And then here's where you set the pins. So SWD have clock and data, and this is GPIO 25. That's like the BCM GPIO 25 and BCM 24. So you can set this, again, to anything else you want, but it's just kind of cool. You just start with 25 and 24. Pin 18 is reset, but again, you can change that if you want to use 18 for PWM output or NeoPixel output. And then there's also the Raspberry Pi 1 Native, which has a different peripheral base. So that's like how if like the Pi 4 comes out, it has like a totally different chip with a different peripheral offset, you would change it. But it's basically, I'm pretty sure it just goes in and like twiddles pins. And then there's also under chip, Atmel, there's just at 91. So there's like a bunch of different chips and scripts. I mean, like every different, here's all the targets. So this is all the chips it supports, from the LPCs to the AT-SAMs to a ton of STMs, OMAPs, Altera, Armada, TI, DSP, Dragonite, CC, some more TI chips. So a bunch of chips, and hopefully, if you have a chip, please make a config file for it. Let's just look at really quickly what the AT-SAM config. So I guess it just says, what endian, the work area size, but how much buffering you use. The actual like special commands, I think, are still programmed in. Like I don't think this defines the special commands here. Maybe that's in the tickle code or something. And then there's NRF51 with ST-Link and without. Anyways, it's all good. So we can go into Bootloader back here. Okay, so you've programmed it in, and here is that GPIO connection. So you will make your connections. You saw I have little wires going from the Raspberry Pi to the M0 chip. Ground to ground. I actually don't connect. I connect power through USB. I just power the program through USB. You don't have to, if you want, you can power the chip direct from the Pi, but I just connect USB and have it done that way. Reset if you need a reset pin. And of course, there's all 3.3 volt logic. If you have 5 volt, 1.8 volt level shift, clock is one directional, but the SWDIO is bidirectional, so you're going to have to figure that out. Like, I don't know, maybe the TXB series would be good. So you'll want to make a directory with your config. So, oops, that's the wrong one. So let's look at this config file. So you first start, and I'm also kind of learning this. There's probably mistakes in these configs, but they do work. You start with telling it what configuration for the interface, and then you tell it you're going to use SWD. You set the chip name. It's just kind of nice. You're telling it this is the exact submodel. And then you tell it, okay, I'm trying to connect to an ATSMD family. I'm not sure exactly what this is. I got this from the tutorial. I might remove this later. You tell it how much to set the reset pin. I think this is in milliseconds. The delay and probably the delay after asserting, deasserting, and then the delay for asserting. And then you have basically this list of commands that tell it what to do. So I'm just going to start with init, which I guess initializes the system, targets, checks what targets are connected, and then reset, which means put the device into reset, which means you can start programming or debugging. And then I commented out all these other things, which I'll get to later. And then I'm going to open in this window. Window's broken. Let's duplicate this session. Okay, so log into the Pi. And then in that directory where you put the OpenOCD.config, you can actually just run sudo OpenOCD, and it will actually connect and find the chip, and then it waits. I'm trying to remember. I think this is correct, because now we can telnet. Yeah, so it's a little. You have to kind of learn how to read. It's not arcane. It's just like you have to learn how to read the output of OpenOCD, because it doesn't really tell you what it's doing. It just tells you like what it did, kind of. But it found the target. It found this chip, and it says, okay, I found this breakpoint, found this ID code. I guess that ID code just identifies the chip, and it's running. And then you actually telnet to it, which is kind of interesting. So you can do remote programming if you want. You can set up the Pi as just an OpenOCD target, and you could just connect to it and tell it to find chips. So you can type in stuff like reset, and it will reset the chip. And then you can do certain commands like, I'm trying to remember what there's this guide of all the info that you can get. So, for example, you can do @91 SAMD chip erase. This will erase the chip. And it will tell you chip erased, clearing a lockup, false, resets, basically resets the chip. Again, it's still learning all of these funky things. And then there's some stuff like the bootloader, like you can set the bootloader protection area as well. So like let's say, I'm just going to put this in the background. We want to program in the bootloader. So the bootloader is in a file, it's a bin or hex file. You can type in program. It'll actually say something interesting. It'll say failed to erase the row. The reason is because it's actually a bootloader protection on, I think. So let me check that. Or it could be, whoa. That's interesting. It tells me every command I could run. That's neat. But what I wanted to do is, oh yeah, maybe I could do info. No, I didn't say anything. @samd bootloader, and it will tell me how big the bootloader size is. So it says right now there's a bootloader protection set for 8K. So let me set that to 0. So it's kind of neat. It's like a command line interface for this chip. And then you say, okay, do you set the bootloader? And then let me try programming now. I'm gonna have to do a reset. You have to figure out for each chip, I've determined there's this kind of magical thing where it's reset, halt, chip erase, reset, unprotect, reset, do another erase. You have to kind of learn what the magic command steps are, because again, this is all hidden in something like Atmel Studio. They don't tell you the commands that they're sending. So you basically set up your config files to be perfect, and then you just copy and paste it. It's a lot like make. These make files. So try programming. Okay, it still says it couldn't, it failed to erase the row. So let's try a reset and then try to program. No, let's do, I have to figure out, was it reset, chip erase, bootloader 0, reset, or maybe it's a chip erase. See, it's you have to figure out, do you erase the chip and then set the bootloading? Do you have to halt? I don't know. Let me check my, I actually had this in my OpenOCD config. So reset, let's see if this works. Chip erase. it says failed to write memory, but it's still erased a chip. I don't know what that means. Not sure. Set the bootloader to 0, and now you can hopefully program this in. Interesting. This doesn't work. Yeah, this is kind of fun. And then sometimes you do like sometimes they do a power reset for fun. I don't know. Let's see if this helps. Playing with fuses, sometimes you can break your. So init reset. Okay, did find it. And then at 91 samd sm bootloader. What was it again? Sam bootloader. Just come on. Why don't you program? Interesting. It failed to erase a different row. Okay. Now I'm getting different errors than before. That's kind of cool. So you basically, you learn like the magic list of commands required. So this worked before. Let's see if it works again. You can also just tell in the OpenOCD conf, you can tell it like all the commands you want to do. So this worked before. I don't know if it'll work again. So let me quit OpenOCD, and then I'll just run it. And then when you put shutdown at the end, yeah, now it's like failed to erase a different row. Could be a different, I don't think I set any protection fuses. But yeah, now it's program failed. Oh, that's so sad. All right, well, it worked before. So probably like some delay maybe I have to add in, or like another reset. So you gotta like, I'm still kind of learning this, like where do you put in what commands to get it into the mode you want. So that's the @samd21. Also, I did mess around with this, with the fuses quite a bit. So the other chip that, this one is actually even more finicky to play with. This is the NRF51A22. And by the way, like one of the nice things about the J-Link is it like kind of like solves like all of this, like when do I reset, what do I do? I think it knows enough about, like there must be some settings inside that it kind of never has this issue. Like it seems to always just sort of work. So that's what you're paying for when you get a J-Link. But with, okay, so can you go to the overhead? I'll try to get this one working. This is like 4 hours of yesterday was just like noodling in OpenOCD. That's what the OCD stands for in OpenOCD. So this is a BLE module with the UART and then USB, and then I got a little SWD connection on the back here. And same SWD connection. This one actually has a reset, which I didn't connect. Maybe I should have connected it. But the NRF does not have, I think, does it have a reset? It does, but it multiplexes it. But we'll set it and we'll see how that goes. So I was also working on this one. So this this program, very similar. You set up the interface. Oh, can you go to the compy? Sorry.
You want multiple views? Or?
Yeah, you can do multiple views. So for this one, you also set the Raspberry Pi Native config, set the chip name. For this, there's a caching issue. So you have to set the work area size, basically tell it not to cache or buffer any data. And then the commands that I found that worked before to program is init reset halt, NRF51 mass erase reset halt program verify shutdown. So we'll see if this works. Make sure I'm not running OpenOCD. Okay, that actually worked, so that's pretty cool. Can we go to, yeah, so so with this one, it it basically sets up the OpenOCD connection, connects at 1 megahertz, and it's really fast. I get programmed the chip in like under a few seconds. Okay, it says got the bitbag driver connected. It found that ID code, found the chip, because once it says like it has the breakpoints and watch points, that's kind of how you know it works. Halted the chip, tells you, okay, this is your looks like your pointers, and then it identifies the chip itself and erases the flash. This is a mass erase, which is a special command that erases like everything. Reset halt again, so that's here. got it back to halt, and then you program the chip. It auto erases. Even though it says auto erase, you still have to do the mass erase beforehand. Just like I figured that out. And then it says, hey, I don't have a lot of working area, so I have to actually do slow memory writes. It's something about the NRF51822. It really needs to write 1 byte at a time or something. And then it writes 13K of data in 1.1 seconds, so really, really, really fast. So that's pretty cool. Program finished, verify started, and then it verifies in 0.1 seconds. So the speeds that we're talking about here are way, way faster than you would program with almost any other interface. If you use the GPIO under Sisyphus, it still is pretty fast. It'll probably take a couple seconds. But I was able to erase the entire chip and program the entire chip in like 2 seconds, which is amazingly fast. And I think it actually is even a little faster than the J-Link or ST-Link because there isn't the USB startup time. Like you don't have to like set up USB connections and timeout and make sure that like your buffers are all working. And also, especially if you are doing this slow memory write for the Nordic chips, you're probably like sending 1 byte back and forth like per packet. With the USB, you're going to slow it down because you have to wait 1 millisecond or whatever for each transaction. With the native pins, it's really fast. So lastly, I thought we could scope cam and just show this scoped out. So I'm going to scope onto the clock pin.
Do you want the computer at all, or do you want to?
Sure, it doesn't really matter. Okay, so let me get that. Oh, come on. Set to 0. There we go. So let's see how fast this goes. Okay, it's a little slower than that. And then, let's see if I can measure. I don't know if it's going to be able to measure the frequency fast enough. Looks like, yeah, about 1 megahertz. So incredibly fast. 1 megahertz, you're not going to get that from even a bootloader or like native USB. That's going to be tough. And it just like clocks the pins like extremely quickly. Then after you're done, you have your program board, and then you can connect over USB and do whatever functional tests you have to do once the firmware is programmed in. So yeah, the Nordic, I spent a couple hours and I totally like found this like magic, like these commands in exactly this order, and it has to be like reset, halt, not reset, halt, and then like you mass erase and then reset. The SAMD21, I'm still kind of figuring out, like sometimes having the reset line connected helps and sometimes it doesn't. So I might have to like add delays or whatever just to figure out what is this path that will let me consistently program them. But once that's done, I'll be able to make a hat, like basically something that goes on top of a Raspberry Pi, that when you clamp it down and press a button, it will like program the chip in 2 seconds and then test that the bootloader works, and you'll be able to have these feathers much faster because they're very popular. So we have to be able to make these very, very quickly. So that's what I'm doing. But I was like, I should learn about OpenOCD anyways. So I wrote a tutorial while I was learning about this wondrous process.
Okay. Now I'm going to ask you some questions.
Yeah.
And because I think that you just dumped a bunch of information.
That was a lot of...
And for the people who make more than 1,000 of some type of board, this was probably the most interesting thing in the world.
I know, for like all three of you.
Yeah, but for people who are tuning in and maybe they're just doing short runs, or they're just interested
there's one chip, yeah.
Or they're just interested in this. So the way you discovered this was you started poking around in the kernel that the Raspberry Pi uses.
No, I actually didn't have to do any of that.
You didn't have to do anything.
Somebody already did it. I was going to. I was like stealing myself for like, okay, I'm gonna add like native GPIO bit-bang support to OpenOCD, but then like I downloaded it and I noticed that somebody, like it was an option. I was like, that's neat. Like it's already done.
So that's one of the neat things about open source. So it must have been useful for someone. It got put in. Yeah. And now it's available.
But I didn't see any tutorials about it. Like there's no documentation. Like whoever did this. I mean, I didn't look at GitHub and whatever SourceForge and see who added this code.
Yeah.
But because I was Googling for it, I didn't find anything, so I assumed that I would have to write it. I did see the system, the file system GPIO, but this is still handy for people even if they're only programming one chip, because let's say you don't have an ST-Link, or maybe the ST-Link doesn't work with the chip you're programming and you don't want to spend $100 or more on a J-Link. If you have a Raspberry Pi, you can program like pretty much any of these chips that OpenOCD supports, and it supports a lot of them. So you can get started programming very, very fast, and you can set it up as a debugger, and then you can use your desktop computer to debug and program like through the Telnet interface. So I think that's kind of neat.
Yeah, and for folks like us who make testers, this is a game changer.
This
right?
is exciting for me, yeah, because I like the ST-Link and the J-Link, but I really wanted something, and we'll show it off when we get it. I made this hat that you can put the Feather M0 on and we'll clamp it down, and then you'll just press like a single button, and in 5 seconds it'll program the chip. Right now what we have to do is you have to get a laptop, and you like hook it all up to the laptop, and then like you log in and the laptop, and you run from the command line, and it's very fast still, but there's just like, you have to worry about the laptop. Like the laptop can crash, or it can have the different.
Can never automate it.
Like for example, El Capitan came out, and El Capitan doesn't work with the ST-Link.
Yeah.
You know,
so there goes your testing suite.
So like everything was great, and then El Cap came out, and then suddenly people upgraded in Fab because they were like, well, I want to have the latest operating system, and also like the App Store tells you to do it, and then all of a sudden the ST-Links don't work. And actually really like them, and we have like 20 testers, so it's kind of like, well, I could get a bunch of J-Links and then rewrite all the code, but I thought, you know what, I eventually you have to, I've noticed that you can make testers that are based on laptops, but eventually you want to transition away from that, and something standalone where if it's a Raspberry Pi, you can make 6 of these, and you just clone the SD card, and it's identical hardware, it's an identical software setup, it's not going to auto update, it's not going to install Windows 10.
Yeah.
It's not going to get malware. It's not going to go on the internet. Like, it's clean.
Yeah. And like your tester's only $35. I mean, technically.
It's nice.
Yeah.
It's and if it breaks, I don't feel like And another thing is, remember that story that Bunny said about like having to get a laptop into China?
Yeah. So this is a common story. So people who do any type of manufacturing over in China, you may have designed it in the U.S., but eventually, if you get your tester over there. And the way things work with China is you might not be able to just send it because of the way their imports work. They would much rather export computers than import computers.
Yeah, you can't, like for a lot of countries,
computers come out, can't go in.
You can't, like when I'd go to Israel, we'd have to register your computer when you entered the country, and they'd stamp your passport, and if you didn't leave the country with that same computer, they'd fine you. Not fine you, but they would basically charge you for the import tax, or whatever, and the import tax can be insane. It can be like 50% of whatever perceived value. So for making these little testers, I ship them. And another thing is like if I'm shipping a tester around, or if, like for a lot of people, like they're maybe manufacturing in China or they're manufacturing in Mexico, they're moving testers around, or if I'm sending a tester to one of our remote people, sending a laptop and making sure that it's exactly the same setup is like a total pain in the ass.
Yeah. Right?
You can be like, use your laptop, then like, oh, I don't have the FTDI driver's different, or I have like this USB, libUSB 0.1. Oh no, it's the one that was forked. Like it becomes like a mess.
Can you use a Pi 0 for this?
You could. Yeah, there's no reason you couldn't use a Pi 0 as an OpenOCD project. That would have been a cool thing for the Hackaday project.
Someone could still enter that in as a project somewhere.
I think that ended 2 days ago.
There's another one.
But there's a new project. There's always. But you could totally make a cool $5 OpenOCD remote thing. You just plug in a Wi-Fi adapter. It shows up on Bonjour as like OpenOCD.local.
Yeah.
And then you can, you just connect that up, and then you use your computer and get your tool chain set up. Well, there's a lot of tutorials for how to use OpenOCD with tool chains. So like get your Eclipse OpenOCD thing going on. So I'm just learning about this. I just downloaded OpenOCD like 2 days ago, and I'm already hating it. No, I mean, I love it, but
it's your new best friend.
I'm learning a lot about it. It's a joy. It's like a puzzle to figure out all these different chips.
And is there any examples or any things out there that talk about? Because I've never seen. Hey, you use this to make a tester. What information is there out there?
I found. Actually, unrelated, I was looking around for other stuff, and I was like reading my RSS feeds, and I found a tutorial called "Running OpenOCD on the BeagleBone Black," and I was just like, what is that? And I was kind of like, I'd heard of OpenOCD, and I knew it was a way to program these chips.
Yeah.
We do use it. We use JLink a lot. So like again, JLink underneath, you just you run jlink.exe, or under Mac it's called jlink.exe, which is kind of hilarious. .app.
Yeah.
It's called jlink.exe.app. But for the ST-Link, I've been using AdaLink, which uses OpenOCD underneath. But I've never like compiled it myself. But this person's tutorial, I'll pull it up. I pretty much just followed this person's tutorial. They did an excellent job. So thank you to Peter van Hooiwegen. Peter. He has a very similar tutorial on a BeagleBone. And this is from 2005 October.
And what did he program?
He was programming an Arduino Zero. He was burning the bootloader on, which is actually kind of interesting because I think this is an Arduino. Yeah, this is the M0, the Arduino.org one that doesn't have the debugger built in, and so if you want to burn the .cc bootloader onto it, so it works with the .cc IDE, you have to go through a stuff like this. And he's like, it's a pain, but he got this working. And yeah, he figured out this command set. You can also see it from within the Arduino GitHub repository. But so I saw this and I was like, that's interesting. Like I didn't know you could use native pins, but that got me thinking like, I can have a Raspberry Pi and it would be. Yeah,
there's a lot of uses for an on-chip debugger, and this is just one of them. That's kind of interesting that you've now turned it should be a testing suite. Like you can.
Yeah, it's gonna be interesting. I think especially because we're doing so much more with the M0s, and the feathers are just so popular that we just keep selling out. And one of the things is they do just take longer to test, and that adds up. I mean, you're like, okay, a minute. It only takes a minute to like test and program a chip. So what? But if you think about it, that means you can only make 60 an hour.
Yeah.
But you can pick and place, hundreds in an hour.
That's not our problem.
The pick and place is very fast. But
we can place 40,000 components per hour right now. So
yeah, so that's
at
fast.
Least, actually.
But the testing has to be faster, and the seconds add up very quickly.
Yeah.
The difference between a 60-second program and a 45-second, 30-second, 25-second. So I think I can get this down to maybe like 20 seconds or less.
Yeah.
Which is significant if you think like thousands of boards times 40 seconds. It's hours that are saved. So even though I'm spending, I enjoy this. I'm learning a lot.
Yeah. Well, we're also making a video about it. So.
I'm also making a video, and I think other people might find this interesting as well, because I didn't know that there was native Raspberry Pi support. Now the entire internet knows, and I'll post up as I figure out like the magic sequence is for all these chips, because that's the thing that's a little challenging is you getting the configuration files. Is like a little. I'm gonna look. There might be like 1 mega site that's like BitTorrent of OpenOCD config files.
There seems two challenges. One, you have to make sure the chips are in there. Two, you have to then get the configuration information.
But you only have to do that once.
Yeah, and so
this magic path of like erasing, and then of course you get error messages, and you look online, and there's just like posts all over. Like there's just forums, and people are like struggling through the exact same.
Yeah.
Like, how did you know to set work area size 0? Oh, because like if you're mass erase, then it reset, then like. Yeah. It's just like we like.
Yeah. So first, identifying which chips are possible.
Yeah, from the list.
From the list, which there is, you can see.
Yeah.
And how would you ever add another one in?
If it's related to an existing chip, like let's say Like the
M0 got in there.
The ATSAM series, it's like a series.
Okay.
So it's a lot easier because somebody, and here's the thing, I don't actually know where the commands are listed.
Yeah.
Maybe like somebody sniffed a JLink or something. Like Segar has them all. Like every chip company goes to Segar and tells them what the commands are, because like Segar is like they're the gold standard. And then there's also eDebug, which Atmel, the companies always have their own as well. But unlike I looked through the AT7D datasheet, I didn't see it. With the AVR datasheet, like the Atmega 328, which is I can show you, if you go to the Atmega datasheet, because we did this before, if you go to memory programming.
Yeah, I'll go to the bigger screen. They include it?
Yeah, they actually tell you the commands. Like literally they tell you like, here are the bytes that you send over SPI. Here's how you wire it up. And here are the bytes you send. This is the command byte, chip erase. You send that command and it erases the chip. So like it's very easy, write EEPROM. And they tell you like how to enter programming mode. Apply 4.5 to 5.5 volts. Set reset to 0. Well, actually that's
Okay, so
like they tell you like
big ups to Atmel on their Atmega 3204 datasheet.
Yeah, like and
That's
all
helpful.
the AVRs have very similar stuff. And then you can look at AVR Dude. They kind of figured this out. Like they have the settings for each chip, and you know they're slightly tweaked, the page size, but the overall commands are the same.
Yeah.
Erase chip is the same for all.
Do the chip
panels.
manufacturers do kind of the same thing? Can you kind of guess?
I think that some of the basic SWD commands. Okay, so it's a little bit like SPI Flash. This is another like enjoyable thing.
Yeah.
So SPI Flash, there's like the JEDEC standard. So reading 1 byte, writing 1 byte, and getting the chip ID is standard. Like those 3 commands.
Everybody agrees on that one.
Everyone agreed like this command is like erase the byte. Every chip has this to read, this to write. However, like when every chip fab, each SPI Flash chip manufacturer then goes totally bonkers with like special commands like page write and protect chip and fast erase and you know scramble and give me the temperature and like random entry, you know, like they'll come up with special extra commands. So even though they always support like this JEDEC standard, then they kind of go crazy, and then because that's how they compete. Because if everyone had the same command set, it would just be pricing. So instead, what they do is they say like we have the 1 byte chip erase, so you can like fast erase, which is better than like the other companies' chip
Auto
erase.
encrypt. We also include a backdoor. Wait.
Yeah.
Oh, we're not supposed to talk about
Stuff like that. You know, they have the protection and unprotect. So it's the same thing. I think I haven't looked at the details of SWD. I'm interested in, but I think that some of the very basic, like this SWD ID code, like to get the ID of the chip, that's going to be standard. So like the way that you query the chip for what chip are you is going to be the same.
Yeah.
And then maybe like write 1 byte to, and like the register writes and reads, but then beyond that, I think it just goes like squirrely.
Okay. And this, folks, is why hackers love doing electronics, because you are just trying to hack the Gibson every single time.
Yeah, I mean,
You're just like, hey, Chip, talk to me.
I was talking to K-Town, because K-Town, like, you know, he's done so much stuff with the
Yeah.
Cortex M0, and he's worked at companies that like design chips with Cortex M0, and I said, hey, like, how hard would it be to make like a bit banging, like Arduino that would bit bang SWD? And he said, you do not do this. He's like, do not get down this rabbit hole. He said, he said, you know, like he's like, oh, let's check out OpenOCD, and you know, you can use a Raspberry Pi or something with an ST link. So he kind of pointed me down this path. He's like, well, I don't know what the fastest way, but you don't want to bit bang SWD. It's totally, you end up rewriting OpenOCD basically, and there's no real way to do it. Although another interesting thing is if you look at the design of the TC 3.2, there's the bootloader chip. That is an all-in-one SWD programmer, because when you press the reset button, you see the chip is connected to reset and SWD and SWC lines. When you press a button, there's a little helper chip. And from what I can tell, when you press that button, it tells that little helper chip to erase the main chip and program in the bootloader.
So it sends a command.
Yeah, so it's a little helper.
Okay. This is neat.
Weird.
Yeah, this is neat, because I know what this means. We're just going to have a whole slew of testers that probably will speed things up by a third or more.
Yeah, and also another cool thing is you'll be able to run them in parallel.
Yeah.
You know, like the people are like, oh, why don't you do like batch, like you do 10 at a time. You can't do that if you can only have 1 ST link or 1 J link connected to a computer. But if you have standalone testers, you can, I mean, it's tough. If it takes less than 30 seconds, it's not worth it, because it takes the same amount of time to put it in and out of the tester. But you could, in theory, have an entire panel, clamp it down, and have parallel programmers. I mean, it's all possible.
Okay. And with that as your desk of late data, thank you so much, folks. We'll be broadcasting probably over the weekend. Tomorrow is usually Desk of Tony D. Watch that on Twitch. It'll also be up on YouTube later. And
maybe we might do something. I got a
we have a
package.
few things. We've got the Learning the Art of Electronics book that we got to go over. We got a Bullport package that came in the mail.
Club
Yeah.
came in today.
And we actually have a ton of stuff. So we got plenty of things going on. So, all right, folks.
Unending. All right. Post your super cool 0-day OpenOCD config FTP sites in the comments and YouTube, and I'll check them out.
Yeah.
I hope there's just like some like cool FTP sites. It's like, get the hottest 0-day OpenOCD configs.
Yeah.
Greet.
New York's hottest club is OpenOCD.
Yeah.
We've got M0s,
Yeah.
SAM R21s. You name it, we got it. Okay. All right. Thanks, everyone. We'll see you later, and thank you for supporting Desk of Data. Pick up an electronic kit or more.
Pick up an ST-Link or a J-Link or an SWD cable.
As you can tell, this is all we do. So we'll keep doing this as long as we can pay the bills. Thanks, everybody.
Good night, folks.
Bye.
I'm tired.
Yeah.